Students, this is the Solubility Equilibrium lab. Before we can get into the data collection portion of this lab, we need to talk about a lab technique that is used in this lab that's really important for understanding it. That technique is called serial dilution. Serial as in S-E-R-I-A-L, like a series of things, not cereal like your breakfast food. Okay, and dilution, meaning we're going to dilute ions as we go on in series, one after another. In part one, we're going to combine hydroxide ion with a serial dilution of calcium ions. In doing this, we're going to take 0.1 molar solutions of calcium nitrate, which delivers the calcium ion, sodium hydroxide, which delivers the hydroxide ion, and when called for, we'll add water. We'll do the mixing in a chemical well plate like this, just a place where you've got several cylinders, several containers, to easily make mixtures and observe without having to get a whole bunch of beakers and things like that. I also have a piece of black construction paper, which serves as good contrast because the product of mixing calcium ion and hydroxide ion together is a solid white precipitate, calcium hydroxide. Well, a solid white precipitate shows up really well against a black background. Let's talk about how we'll make the dilutions. We have 12 wells that we're going to make use of, and they're all on that chemical well plate. They may not all be in a row, but you can go from one row to the next. And we're going to take 0.1 molar solutions of calcium and of sodium hydroxide. We're going to start by putting 5 drops of 0.1 molar calcium hydroxide into well 1. I'm sorry, calcium nitrate. And I'm only going to abbreviate that with calcium. How about that? And we're going to add that to well 1. I'm also going to add 5 drops of calcium ion solution into well 2. In addition, I'm going to add 5 drops of water all the way from well 2 to well 12. So all 11 of those wells are going to receive, oopsies, 5 drops of water. Now, the wells have a total volume of about 10 milliliters or 10 drops or so until they fill up. So now here's where the serial dilution part comes. You've got some calcium ion in well 1 that's not diluted. You've got some calcium ion in well 2 that is diluted. And I'm going to have you take well 2's contents, mix them together, and then take 5 drops of well 2 and add it to well 3, where there's already 5 drops of water. Mix it together, and then take 5 drops of well 3 and add it to well 4, where there's already 5 drops of water, and mix it together. So the concentration of calcium in well 2 is going to be half of what was in well 1. The concentration of calcium that's in well 3 is half of what was in well 2 because there's already 5 drops of water. The concentration of calcium ion in well 4 will be half of what was there in well 3. The concentration of calcium when you transfer 5 drops of well 4 into well 5 is going to be half of what was in well 4, and so on in series. So we're going to take 5 drops of well 5's contents, mix and transfer. 5 drops of well 6, mix and transfer to well 7. 5 drops of 7, transfer to 8. 5 drops of 8, transfer to 9. 9 to 10, 10 to 11, 11 to 12, and then, this is interesting, at the very end, after mixing well 12 together, we're going to discard, that is, throw away down the sink, 5 drops from well 12 because we don't need it. There's not a 13th well. All right, so we'll have a serial dilution of calcium ions. Now, for the rest of this, remember, we've got to make a solid white precipitate, calcium hydroxide. Well, you're not going to get calcium hydroxide unless you add hydroxide ions. So we're going to now take this beautiful serial dilution of calcium ions, and to every single well, 1 through 12, we're going to add 5 drops of hydroxide ion. The hydroxide ion is provided by the sodium hydroxide solution. So remember, we've got decreasing concentrations of calcium to which you're adding identical concentrations of hydroxide ions. Whichever well is the first one that does not show a precipitate is the well that we'll presume is a saturated solution. And all we need for data is to note the well number when the saturation point occurs. So in well 1, the concentration should be high enough that there's definitely going to be a precipitate. In well 2, very likely a precipitate. By well 3, I'd say likely. By well 4, maybe. By well 5, don't know. By well 6, seems less likely. Remember, you're going, the concentration of calcium is half as much each time. By well 7, I'd say unlikely. By well 8, I'd say very unlikely. By well 9, I'd say very, very, very slim chance of having a precipitate. We're simply going to note the well number that's the first one that did not have a precipitate. Now for part 2, the process is quite similar. In part 2, we're going to take the same 12 wells after cleaning them out and drying them, have a nice clean start. But we're going to combine calcium ions with a serial dilution of hydroxide. So this time, let's describe it again, but with the ions flipped. To wells 1 and 2, we're going to add 5 drops of hydroxide, as provided by the sodium hydroxide solution. Then we're going to add to wells 2 through 12, we're going to add 5 drops of water, kind of like what we did in the last serial dilution. Wells 2 through 12 are all going to receive 5 drops of water. And then remember, each well has a total volume or a maximum capacity of about 10 drops. So if in well 2, we've got 5 drops of the hydroxide solution and 5 drops of water, that means that we've got to mix and transfer 5 drops into well 3. And then mix the contents of well 3 and transfer 5 drops to well 4. Mix well 4, transfer 5 drops to 5. Transfer, mix and transfer, mix and transfer, mix and transfer, all the way down the line. And then, just like our last serial dilution, after well 12, we're going to discard 5 drops. We will have produced by that point a serial dilution of hydroxide ions, where well 1 has a concentration of 0.1 molar, well 2 would have half as much, 0.05 molar, well 3 half as much as that, 0.0125 molar, well 4 half of that, well 5 half of that, well 6 half of that, and so on. Half as much of the concentration with each well. To that, we're going to add, so now we've got a beautiful serial dilution of hydroxide, but we haven't gotten a way or a chance to make the precipitate calcium hydroxide. To every single well, wells 1 through 12, we're going to add 5 drops of the calcium ion. Remembering that we're starting in well 1 with the highest possible concentration, I'd say it's very likely that you'll have a precipitate in well 1, and well 2, still quite likely. By well 3, pretty likely. By well 4, maybe. By well 5, maybe. By well 6, kind of unlikely. By well 7, I'd say unlikely to see a precipitate. By well 8, 9, and so on, a very low chance of a precipitation occurring. Your job is simply to note the first well that does not show a precipitate. And based on the data we collect, we'll be able to calculate a KSP value for calcium hydroxide. Let's see how the data turns out. Okay, students, I want to show you what the well looks like. In part 1 of the lab, the first well that did not show a precipitate was well 4. Now, if you look closely, you can kind of see some cloudy white materials. So well 4 was the first well in part 1 that did not have a precipitate, and it was well 5 in part 2 that did not have a precipitate. We'll use that in our calculations. Okay, let's take a look at the data portion of this lab. You'll want a calculator for this. We were analyzing the breaking apart of this salt, the white precipitate calcium hydroxide, whose ions are calcium, and because there's a subscript 2 for hydroxide, to make a balanced equation, we need 2 hydroxide ions. If you were asked to write an expression for the equilibrium constant for this reaction, you'd have no trouble. You'd write K, and since this is a solubility equation, you might put the subscript SP, which has no mathematical meaning, but it's helpful to remember, okay, this is a solubility equation. And we would put the concentration of the reactants multiplied together, and since there's a coefficient 2 in front of hydroxide, we'll square the hydroxide concentration. That'll be important when we go to calculate K. Now, there were 2 parts to the lab. One, we were combining the hydroxide ion with a serial dilution of calcium ion. And in that part, we found that the first well that did not have a precipitate was well number 4. So it was it started out wells 1, 2, and 3 all had a whitish precipitate. The first well that lacked that precipitate was well 4. In part 2 of the lab, we were combining calcium ions with the serial dilution of hydroxide. And in that case, the first well that did not have a precipitate was well number 5. Based on just that data, we're going to be able to calculate a value for KSP from the part 1 data and from the part 2 data. And then we'll probably average the 2 and see just how close we are to the accepted KSP value for calcium hydroxide. So starting with part 1. The data table looks big, but it actually is going to go quite quickly here. We had 12 wells. And what they're asking us to calculate is the concentration of calcium before we added sodium hydroxide ion. So if you remember, well 1 had 5 drops of 0.1 molar sodium hydroxide. Well 2 had 5 drops of 0.1 molar sodium hydroxide, or I'm sorry, calcium nitrate, plus 5 drops of water. So that means you had half as much. In well 3, you took 5 drops of the contents of well 2 and added that to 5 drops of water. So it would be half as much again, 0.025. In well 4, it was 5 drops of the contents of well 3 mixed with 5 drops of water. So the concentration again gets cut in half to 0.0125. As we work down this column of data, we're just dividing by 2 every time. Certainly consider using an Excel spreadsheet in this case. I'm going to round to 2 significant figures going forward. All of those concentrations are the result of serial dilution before we added the sodium hydroxide. When we added 5 drops of sodium hydroxide, then the calcium ion concentration went down by half once again. So to figure this next column where it says concentration of calcium after adding the NaOH, simply shift what's 1 column over and 1 line down up to that box. So in well 1, it was actually 0.05 molar after you added the sodium hydroxide. And in well 2, it was 0.025 molar after you added the sodium hydroxide. And we'll just do a little data upkeeping here. All we're going to do is add or take the number that was in the column to the left 1 row down and put it into our box to the right. Believe me, this is the hardest part, and then it'll get very easy from here on. Okay, last little bit. We weren't making in part 1 a serial dilution of hydroxide ion. Instead, we were adding 5 drops of 0.1 molar sodium hydroxide to all 12 wells. Well, if you had 5 drops of something else, some dilution of calcium, and you're adding 5 drops of 0.1 molar hydroxide ion, when mixed or after mixing, the concentration of hydroxide for every single well is 0.05 molar. So we've got our numbers worked out. Next, we're going to consider which was the first well that did not have a precipitate. Remember, the concentrations are going down. So high concentrations down to lower concentrations. So where there's a high concentration, we certainly had a precipitate. Wells 1, 2, and 3 all had precipitation occurring. But well 4 was our first one with not a precipitate, without the precipitate. And it was nose all the way down. So thereafter, if the concentration is less, there's going to be no precipitation thereafter. So our first well without a precipitate was well 4. And what we want to do is say, okay, with those concentrations, can we calculate a value for K? Absolutely. Since we know that our expression for KSP for this reaction is the concentration of calcium times the concentration of hydroxide squared, and we've got a concentration of calcium in well 4 of 0.00625 molar and a concentration of hydroxide of 0.05 molar. Don't forget to square that. We're simply going to plug that into the old calculator and see what our value for K is. And I get 1.56, 10 to the negative 5th for our part 1 data. Now, we're not quite finished. We're going to do the same process again for part 2. Remember, part 2, we were adding calcium ion to a serial dilution of hydroxide ions. So it's going to look exactly the same as the data table from part 1. In fact, I even encourage you, if you want to do this, to just copy the numbers from the first column of the part 1 data table into the part 2 data table. And the reason you can do that is the initial concentration for both the calcium solution and for the hydroxide solution was both 0.1, same concentration initially. So I'm actually just going to copy column 1 from the first data table to the second data table. That's the concentration of hydroxide before the calcium nitrate solution was added to each well. After the calcium hydroxide was added to each well, the volume doubled while the amount of hydroxide ions stayed the same. So once again, we would divide by 2 to find the concentration of hydroxide in each of the wells to find the concentration after mixing. To do that, I'm just going to take whatever's in the second row of the first column and put it in the first row of the third column. So 0.05 down in the dilution 2 before mixing becomes 0.05 in the first row after mixing. And I'm just going to copy that all the way down. See how this goes more quickly after you've done it the first time? To calculate the concentration of calcium after mixing, consider that we were adding to all 12 wells 5 drops of 0.1 molar calcium to 5 drops of some serial dilution of hydroxide. So the calcium ion concentration would be half of 0.1, which is 0.05, all the way down the column here. Lastly, when we start with high concentrations of hydroxide and work towards lower concentrations. We're going to move from a guarantee of having a precipitate to an area where precipitates are maybe yes, maybe no, to definitely not. Well, the first well that did not have a precipitate for part 2 of the reaction was well 5. So we'll write yes, precipitation, yes, yes, yes. And then the first one that was a no was well 5. And it's no's all the way down to well 12. So let's circle and star well 5 in this case. And the two concentrations we want to focus on are the hydroxide in that serial dilution of 0.003125 and the concentration of calcium of 0.05. Remember, the KSP expression for this reaction is calcium ion concentration times hydroxide ion concentration squared. Well, let's plug in our numbers. Now this time the hydroxide is the dilution and the calcium is 0.05. So I'm going to write 0.05 times 0.003125 squared. We've got to type that into the old calculator here. We get, if I'm rounding to two significant figures, 4.9 times 10 to the negative 7th. So after doing all this calculation, we got a KSP value from part 1 our part 1 KSP value was 1.6 times 10 to the negative 5th. And for part 2, we get a KSP of 4.9 times 10 to the negative 7th. Now, you might say, gee whiz, Mr. Gaffey, realizing that our main focus here is on the exponents, -5 and -7. Are they close to each other? I mean, theoretically, they should be. You know, they're two they're two orders of magnitude away from each other. In other words, they're about 100 times different. You might say, gosh, that's a big difference. And it is, but it's not terribly obscene. You could have bigger differences in KSP values. And you could look up, for instance, the accepted value for the KSP of calcium hydroxide and make those comparisons. But I would say there's a lot of sources of error in this lab. For one thing, we only dealt with 12 wells, and the only way that we move from one well to another is by cutting in half the concentration. It's not like we took a little granular approach and said, let's dial down the concentration by 0.1 in each of the wells. No, we were cutting it in half each time. So there's quite a dramatic difference in each of the wells' concentrations. So that's one source of error. Number two, you're using your own eyesight to trust that you can identify the first well without a precipitate. That, again, is kind of dicey. You could use things like a spectrophotometer to see just how translucent a solution is rather than your own eyesight with a sheet of construction paper behind it. But nevertheless, the fundamental mechanics of the lab went well, and I'd say these are respectable numbers. So thank you for your good work. I know the calculations were pretty intense this time. Hope it was fun for you.